Hello everyone, welcome back to the channel. So today we are going to see another property of perfect squares in number theory, where we are saying that if n is a perfect square of a positive integer and n belongs to z plus with n congruent to 0 mod 10, that means the last digit of n is 0, then n is congruent to 0 mod 100. That means the last two digits of n should be 0 0. Pretty interesting. That means I'm saying that we can never have one single 0 at the end of n if n is a perfect square. Because if that's the case, then n won't be a perfect square. And if n is a perfect square that's ending with 0, it will have to end with two zeros. Simple property, but this gives us an idea that there's some factor of 10 in n if it ends with 0, and the squaring kind of reflects as a factor of 100. But once again, how do we prove it formally? So just like I usually start with n equals k square, and I've done this for other two videos on perfect squares, so I'll try to link them in the description. This is usually how I define things. N is k square where k is also a positive integer because n was a positive integer. And in this video, I'm not really taking examples and going through all of that. This is kind of a much smaller concept. So k is root of n, square root of n. Just to be consistent with what I've done in the other videos, but I don't really need this or this perhaps. But anyway, and if k is a 2j plus 1 digit number, so there are 2j plus 1 digits in n. Once again, just like my other videos, I'm trying to define properties of k, whereas the original properties is something we have to define for n, but we'll get there as usual. And j will be 0 or a positive integer. So because it's just a number of digits, it's 0 when k is a one digit number, and the digits of k are represented like this. That's also something we have used before, and the property which I'm not going to prove, I'm directly going to use from the other videos of perfect squares, is k will be congruent to a0 mod 10, because a0 is the last digit, so when I divide by 10 it gives me a0. But now we had also done this for n. I remember in that video I had expanded n as k square and written k in a form like this. The property was this, where I had represented k in this form. Should have written this earlier, probably. Anyway, this is how I had represented k in terms of the digits. And then we say that since everything has a factor of 10, when k is divided by 10, you get a0. And I had shown that n equals to k square. I had expanded, I had multiplied k into k, and this then expanded these terms and then arrived at this result that I will be directly using here. So we are saying that n is congruent to 0 mod 10. That means n is common to 0 mod 10, that has to mean that a square is equal to 0. And this is only possible when a0 is 0. And there you go. I can only have one possible value of a0. That means k is automatically constrained now because a0 is 0 and everything else has a factor of 10 in k. So if I just write that factor 10, I'll have something like this for k, and a1 is left out because I've taken the 10 here. And perfect, this is something like 10m or something where m equals this. So k has a factor of 10, and we can see that n, that is k squared, will be the square of this. Pretty easy to see where this is going. Is 100m squared, so that has to be, since you have a factor of 100, this will leave a remainder of 0 mod 100. And there you go, we have what we set out to prove. But I will mention something a bit further, and I say that if n is, just to get a more clearer idea about why the last two digits are 0, because it's already divisible by 100, and intuitively you know that if it's divisible by 100, the last two digits will be 0. But I'm still going to try to prove it or present a way, a formal way of expressing that. J prime plus 2j prime plus 1 digits in n, because most likely j prime has to be larger because n is the square, so n will have more digits than k. And I've already used j here, so I had to use j prime here. And n is probably a number of this form: 10 j prime bj prime 10 j prime minus 1 bj prime minus 1 plus dots plus 10 squared b2. I'm purposefully bringing in this in because I need to now deal with hundreds. So I'm writing that 100 term as 10 squared that I never wrote before in the representation, plus b0. Well, if this is divided by 100, you can see that every term on the left of this has a factor of 100. So n has to leave a remainder of 10b1 plus b0 mod of 100. Now b1 and b0 are digits, and I can show that this term b10b1 plus b0 will always be less than 100. Why is that? b1 and b0 are two independent variables, so for b1 I can choose any integer from 0 to 9, and for b0 it can also be any integer from 0 to 9. So the maximum of this expression will be when both b1 and b0 are 9. So that means 10 into 9 plus 9, that is 99, and that's less than 100. So what do we get here? We see that if it is less than 100, then mod 100 will always leave this remainder, and in that case n will not be divisible by 100. But we already proved that n is divisible by 100 because n is converted to 0 mod 100, n is converted to 0 mod 100. We proved that. So to be consistent with this can mean that this can happen only when 10b1 plus b0 is equal to 0. And now if you're trying to find positive integral solutions where b1 and b0 are numbers between 0, integers between 0 and 9, the only solution for this will be b1 equal to 0 and b0 equal to 0. because we cannot have negative solutions or any fractions here, so both have to be identically 0. And that means b1 and b0 were the last two digits of n, the perfect square, not the root. So the last two digits are 0, hence the perfect square will end with two zeros, and there you go, you have the result. So hope this was useful. Thank you so much for watching, and thanks for being with me as always. Thanks a lot.